This lesson is for section 5.5. This is part 2. We're going to be solving log and exponential inequalities. I think this is particularly a tough subject because it requires you to really know the inequality solving, quadratics, solving rational inequalities, and all that we've done before. It requires you to really have a very good understanding of that in order to do log and exponential inequalities. So it's pulling together a lot of stuff that is review, but also making it, brand new and a little bit more difficult. I want to go through the 3 rules that you're going to use and abide by when you're solving a log or exponential inequality. These rules might not make sense the first time I read it through to you. Hopefully I do explain it well, but you'll get a better sense once you start actually solving these problems on your own about what these rules mean. So first up, when you log or exponentiate both sides of an equation, it does not change the inequality's direction. Okay? So logging or exponentiating an equation doesn't change the inequality. But if you take a log base b of a and it's negative, so it's only negative when a is between 0 and 1, then the multiplication or the division of that equation does change the inequality direction. So what do I mean by that? Well, let's say you have a value and you're multiplying by log base 4 of, let's say, 1/2. The argument's 1/2. Well, this value has to be negative because 4 raised to some power, in order for that to equal 1/2, it must be a negative value. So anytime you have your argument between 0 and 1, it must be a negative value. And in fact, it will end up changing the inequality's direction. Now, the last rule is that when you solve a log inequality, you have to pay attention to the log's domain restrictions. Because a log has a domain restriction, and that's that the input has to be greater than 0, has to be a positive. That final answer of the solution that you get has to be with respect to that original domain. Okay, so we'll go through some problems where we use each of these rules here. In rule 2, I'm actually going to add a question to number 13 just to show you what I mean and demonstrate that. All right, let's start with problem number 1. So in problem 1 or 11, I have an exponential. So this has a domain of all reals. So I actually don't need to worry about this domain when I find my final solution because since it's all reals, I don't have to answer it with respect to anything in particular. So I'm going to solve this trying to isolate the x. So I would divide out the 4, and then I would add the 5, and I'm left with this inequality. Now I want to rewrite this. You don't have to rewrite this, but I want to rewrite that as 1/10. 1/10 to the x power, and then I'm going to take the log of both sides. Now, taking the log of both sides doesn't flip the sign. That's rule number 1. It does not flip the sign. So taking the log of 1/10 on both sides here doesn't change the inequality sign, and since the log of 1/10 raised to 1/10 is going to cancel each other out, I have x is less than log base 1/10 of 7. I'm actually finished with this problem. It's quite easy. I just isolated the x. And since I don't have to answer within respect to a restricted domain, this would be my final answer, and I can write that as an interval from -infinity up to log base 1/10 of 7. Okay, and this is going to have an open bracket because this is strictly less than that number. Okay, now in problem number 12, we have to take a look at the fact that this function here, this log function, has a different domain than we had in the last problem with that exponential. So our domain here is going to be all values that are positive, so 4 minus 5x has to be greater than 0. So when I solve this and I flip our sign here, I get x is less than 4/5. So any value that I get for x must be less than 4/5. So I have to take this domain restriction into account when I solve this problem. So I'm going to raise both sides here. E to the second power on the right hand side, this is going to cancel, leaving me with 4 minus 5x is less than or equal to e to the second power. And now to isolate x, I would subtract the 4 and divide out that -5. Whoops, forgot to subtract the 4 here. Divide out with the -5 and flip the sign here to get e squared minus 4 over -5. So these are values. It's saying x is supposed to be larger than e squared minus 4 divided by -5. However, overall, it also is under the restriction here that x must be less than 4/5. So my interval that satisfies this inequality here is going to be from e squared with a closed parentheses here, or closed bracket, because it's greater than or equal to this number. So e squared minus 4 over negative 5 up to 4/5. And that's going to have an open bracket here because it's strictly less than 4/5. So this would be my solution set for this particular log inequality. Now in number 13, I want you to take a look, and these are basically almost the same type of question. I have 4 minus 5x here and less than or equal to 2, so it's very similar, except for now it's an exponential instead of a logarithmic. So the domain here, the domain is all reals. Okay, and when we solve this and raise both sides, or take the natural log of both sides here, I end up with 4 minus 5x is less than or equal to the natural log of 2. So when I isolate x here and subtract the 4 and divide out that x, or the negative 5, sorry, in front of the x, I flip the sign and I get the natural log of 2 minus 4 divided by negative 5. So because this didn't have an original restriction on the domain here, the answer in interval notation here is going to be the natural log of 2 minus 4 over negative 5 through positive infinity. And of course that has an open bracket because there is no such number as infinity, so we keep an open bracket here. So this would be my solution, so slightly different than what we just saw here in number 12. Sorry guys, but I want to add a problem in here. Let's call this 13b. I really want to demonstrate rule number 2 with you guys, which is when you take the log base b of a and a is in between 0 and 1, that you need to flip the sign. So I'm going to demonstrate that here, and I don't have a problem that does this, so I want to do this with you right now. So let's add a problem. Let's make this, 1/2 to the 3x minus 1 is less than or equal to 2. Now to solve this is similar to yesterday's exponential equation where we took the natural log on both sides. I want to do that here as well so that I can rewrite this now. When I take this on both sides, I'm going to pull that exponent and rewrite this as 3x minus 1 in parentheses times the natural log of 1/2 is less than or equal to the natural log of 2. Now to solve for x here, I am going to distribute both of these. Actually, it's natural log of 1/2 is going to get distributed to both of these, but now I have 3x times the natural log of 1/2 minus the natural log of 1/2 is less than or equal to the natural log of 2. If I want to get x alone, that means I need to move this. This is just a number. It's a constant. It's a real number. There is no variable here, so I would move this to the other side and add that. And I have 3x times the natural log of 1/2 is less than or equal to the natural log of 2 plus the natural log of 1/2. Now, when I look at this and I want to isolate that x, I want to get rid of the 3 times the natural log of 1/2. This is the coefficient in front. That's like saying, again, this is just a number, so this is like 3x, right? To divide it, to get rid of it, I just need to divide by that coefficient. So that's what I'm going to do here. But when I look at this, natural log of 1/2, so it's log base e of 1/2, this has to be a negative exponent in order for this to equal 1/2. So that means that when I divide over here by that value here, I need to flip this sign. So I have x is greater than or equal to the natural log of 2 plus the natural log of 1/2 divided by the 3 times the natural log of 1/2. So that's a problem where we're using rule 2, that you need to make sure you flip the sign when you're dividing by or multiplying by a log base b when a is in between 0 and 1. In problem 14, I want to condense this as one logarithm. So I have natural log of x times x minus 5 is less than or equal to the natural log of 36. Now I have x squared minus 5x, and that's the argument here, is less than or equal to the natural log of 36. Now, since you have the natural log and it's the same base on both sides, that means that your arguments, x squared minus 5x must be less than or equal to 36. Okay. Now, solving this, I have x squared minus 5x minus 36 is less than or equal to 0. I have a quadratic that I can factor, so x minus 9 and x plus 4 are my linear factors, and that's supposed to be less than or equal to 0. This is a total review of a previous chapter. So we're just solving an inequality here, and it's a quadratic inequality. So what I want to do is find my key numbers and test my function. So you're going to test on a number line. Our key numbers -4 and +9. Okay, and I'm going to test from -infinity up to -4, from -4 to 9, and from 9 to infinity. So I choose any number that falls in there, and if I test a number, let's say I choose -5 here. If I plug in -5, I have a negative times another negative, which gives me a positive, so this part here is positive. If I choose a number inside here, let's make that 0. Let's just test 0. If I plug in 0 here, I have a negative times a positive, which overall is going to give me a negative for this interval here. And if I test 10, I would have a positive times a positive to give me an overall positive here. So the only interval that is less than or equal to 0 is from -4 to 9. Okay, and this would normally be my final solution here. However, go back to the original and look at what the domain of this log would be. So the domain here, x minus 5 has to be greater than 0 and x has to be greater than 0. This is actually more restrictive than x is greater than 0. This is saying that x must be larger than 5. So I cannot use values from -4 to 5, right? Those are all not going to give me a valid argument. I have to have a positive input for this log. So my actual solution, so this would be bad. My actual solution would be from 5 to 9. And the reason why on 5 I should not have this closed bracket, I'm going to erase that and put an open bracket here, is because it's strictly greater than 5. Okay? And this would be my final answer here. So make sure you're always answering this in relation to the original domain as well. So you have to look at your original restrictions and answer accordingly. Now, an easier and probably quicker way to have done this same question here, instead of testing your regions, is think about this as a quadratic. You have a quadratic function here, and it has two intercepts, x-intercepts here at -4 and 9. The only point at which this function is negative is in between -4 and 9. So you could have skipped the testing if you just recall, that basic idea from before. Now, in problem 15, we have an exponential function, which means that there's no restriction on x. X is all reals. So when we answer this, and I see I've got e to some power equaling another power, well, or less than another power, that means that -x squared must be less than -24. I'm going to move that 24 to the other side. Actually, let's move the x squared to the other side. So if 0 is less than x squared minus 24. In other words, x squared minus 24 should be greater than 0. Okay. Now, when I solve this, you need to figure out where your two key points are. And to figure out your key points, you have to solve this quadratic here. Now, the quickest way to solve that quadratic is to set them equal to each other and to find that x is equal to positive or negative 2√6. So these are your key numbers. And I'm going to do that using the trick that I just showed you before. If this is a parabola, this is a parabola that's been shifted down 24 units like that, and it has two real intercepts, one at 2√6 and one at -2√6. Now I want to know where those or where this function here is greater than 0. Well, it's everything from 2√6 and on, and everything from -2√6 and on. So the answer here is going to be two different intervals. It's the union of two intervals from -infinity up to -2√6 and from 2√6 to +infinity. And I do have on both of these open brackets because it's supposed to be greater than 0, not greater than or equal to 0. So that would be my solution for number 15. Now number 16 I think is probably the most difficult question on this lesson, because you have to recall some stuff about, and I think these were the hardest problems when we did inequalities. So this is a rational inequality here. This is going back to, I think it's chapter 2, and the chapters are blurring together, but I think this is the hardest question because this was the hardest type of question in chapter 2. So when you see this, you can raise both sides to, or e to, take the exponential on both sides here to cancel this out. But also you can just tell, because the arguments here, that 3x minus 2 over 4x plus 1 has to be greater than 2. So this is the inequality that we're going to solve. Now we can't solve this inequality though, because we can't just multiply by 4x plus 1. Multiplying by 4x plus 1 on both sides is not the way to do this problem, and this is why it's hard, because it looks like it's an easy problem. The reason why you can't do that is because you don't know what the quantity x is. You don't know if it's positive or negative. You don't know if it's going to flip that sign. So you cannot multiply by 4x plus 1. So what we have to do actually here is move this 2 to the other side. So I'm going to rewrite this rational now and bring that 2 to the other side. So I'm going to use a common denominator here of 4x plus 1, so that I can move that 2 to the other side and combine those terms. So I'm going to do that real quick, and after combining my like terms here, I have negative 5x minus 4 over 4x plus 1 is greater than 0. I'm going to factor out this negative from the top and write that as 5x plus 4, the opposite of 5x plus 4, over 4x plus 1. Okay, I'm going to do that before I find my key numbers. The reason why I'm doing that is because I think your key numbers are going to get all messed up if you don't factor out that negative, and when you go to test, it's also going to become a little funky. So always factor out, if you can factor out a negative from both terms, do that, and make the problem a little bit easier on you. Okay, now I know I have two key numbers here. My key number from the numerator is going to be negative 4/5, and my key number from the denominator here is going to be negative 1/4. So I am going to test this rational function. So I'm going to test negative 5x plus 4, the opposite of 5x plus 4 over 4x plus 1, using the intervals from negative 4/5, negative infinity to negative 4/5, from negative 4/5 to negative 1/4, and from negative 1/4 to positive infinity. So these are the intervals that I want to test. Alright, so I'm going to pick easier numbers to deal with, like, let's just throw in negative 1 here to test this left interval. When I plug negative 1 in here, I still have that negative from the outside, and this is going to give me a negative on the inside here if I plug in negative 1 for x. If I plug in negative 1 for x, I get a negative in the denominator as well, so this interval here is negative. The interval between negative 4/5 and negative 1/4. This might be a little bit trickier for you guys to pick a number in there, but I just use like negative 1/2. So if we pick negative 1/2, we end up with the negative on the outside. Here, a positive on the inside. If I plugged in negative 1/2 here for the x, I'd get a positive for this linear term here. And in the denominator, if I plugged in a negative 1/2, I would end up with a negative overall, so that results in a positive. This negative and this negative here are going to cancel out, so I have a positive interval here. And from negative 1/4 to infinity, let's just pick a positive 1. Let's plug in positive 1 here, I get negative times a positive over another positive, so this interval here is also negative. Now, to answer this original problem, I have, let's go back to this, sorry. I have that it's supposed to be greater than 0, so I only have one interval here from negative 4/5 to negative 1/4 that satisfies that original, or I'm sorry, this rational function. However, let's go back to our original log function here. That input, 3x minus 2 over 4x plus 1 has to be greater than 0. So now I have to test here as well. So let me show you guys what you want to look for now. So to find the actual domain of this function, I need to find your key numbers here. Your key numbers here are going to be 2/3 and -1/4 again. So I need to test 3 different intervals, just like I just did here, to figure out where it's greater than 0. Now, just for the sake of your sanity, I went through this. I know this problem's getting really long, and hopefully it's not confusing you. If you just go back and play it over again, hopefully listening to the explanation one more time might help you a little bit. But I tested the intervals here, using our original input here and making that greater than 0. I tested our intervals, and I found that these 2 intervals were positive, so it would satisfy this original input. Now, our answer, our solution, this -4/5 to -1/4, that does fit within this particular interval here, which means that the entire answer solution here, this solution here, is within the domain, the original domain. So my final answer for this problem is -4/5 to -1/4. So real quick to recap, I just want to make sure that you understand these 3 rules. Whenever we log or exponentiate both sides of an equation, it does not change the inequality sign. However, when we multiply by, like in 13b here, when we added that problem, we do need to switch the inequality direction because that value has to be negative. And then problem 3, with almost every single problem here, when it was a log problem to begin with, you have to make sure that you consider the original domain restriction when you answer with your final solution set. Alright, nice job guys. I appreciate you listening, and I'll see you guys in class mañana.